Welcome to Module 10, Spectrum Processors. After this presentation, you should understand the operating principles of equalizers, filters, and psychoacoustic processors. The uses of parametric, graphic, and paragraphic equalizers, and the concepts and application of equalizers for shelving, bandpass, band rejection, and notching. Spectrum processors affect the frequency characteristics of audio. Generally, there's three categories of spectrum processors: equalizers, filters, and psychoacoustic processors. We'll focus on the first two. In some ways, spectrum processors are actually amplitude processors because they increase or decrease the amplitude in certain bands of frequencies. Let's begin by looking at our frequency spectrum. As we saw in a previous module, we can divide the entire range of human hearing into different bands of frequencies. Here we see the range of human hearing arranged by octaves, and our amplitudes arranged as we might find them in an electronic audio signal. Here we've chosen 5 arbitrary bands: bass, low mids, mids, high mids, and our highs. So the concept of equalization is adjusting amplitudes, but only for a certain range of frequencies. For example, I could increase or decrease the amplitudes of any of these bands of frequencies without affecting the others. This is the concept of a graphic equalizer. Graphic equalizers can be made in various configurations: a single octave or 10-band equalizer, and the two most common, a 2/3 octave or 15-band equalizer. Here we see a stereo version or 2-channel version of a 15-band equalizer, and a 1/3 octave or 31-band equalizer. Two methods are used to increase or decrease the amplitudes: either boost or cut, peak or dip, or to shelve. Shelving can only be done at the lowest and highest ends of the frequency spectrum. We'll see what these mean here in a minute. Graphic equalizers have fixed frequency bands. Their bandwidth is also predetermined. The only change you can make with a graphic equalizer is the amplitude or the gain of the frequency band that you're working with. Some graphic equalizers allow boost and cut. Other graphic equalizers only allow you to reduce the amplitude. So another type of equalizer is known as a parametric equalizer. Parametric equalizers are used most commonly in situations where the need to continuously change equalization is most present. Graphic equalizers, on the other hand, are generally used in situations where you set it and forget it. A good example being where you are equalizing the frequency response of a room. Parametric equalizers control 3 parameters: the center frequency, the bandwidth, and the amount of boost, amplitude increase, or cut, amplitude decrease that you're applying. Let's take a look at the 7-band equalizer that comes with Pro Tools to see what we mean by center frequency, bandwidth, and gain. Here are the controls for the 7 bands: 1, 2, 3, 4, 5, 6, and 7. This first control here is set to be a high-pass filter. This means it will pass the frequencies above a certain point. Let's turn this filter on and we'll see from the graph that above 64 Hz, the frequencies are allowed to go through. Below 64 Hz, their amplitude falls off rapidly. Notice that we can change this frequency to just about anything we want. High-pass filters are good for getting rid of low frequencies such as rumble. Our next filter down here, the red one, is currently set to be a shelving filter. Notice that we can shelve the frequencies up, that is, increase all the frequencies below a certain point, or we can shelve the frequencies down, decrease the amplitude of the frequencies below a certain point. What do you think would be a good use for shelving filters? And as you might expect, for the high frequencies, we have a low-pass filter. What differences do you notice between the shelving filters and the high and low pass filters. And we'll just turn this one off. Another type of filter that we have is a band pass or band reject filter. This type of filter operates on a band of frequencies, and we'll use the orange filter to demonstrate this, the low mid-range filter. Notice that I can change the amplitude simply by grabbing the point on the graph and increasing it. I could also change the gain with the gain control down here. This demonstrates controlling the gain. I can also change the frequency for this filter. I can decrease it, or I can increase it. Again, changing the gain, up or down, increasing or decreasing, and of course, as we saw, changing the frequency. But there's one more thing I can change with this filter. All full parametric equalizers can change the center frequency, the gain, and the bandwidth. Notice that I can change this to a very wide band of frequencies, or down to a very narrow band of frequencies. This control is called the Q of the filter. The Q of the filter is the ratio between the center frequency of the band and the bandwidth of the band of frequencies. As such, the higher the Q, the more narrow my frequency band is. The lower the Q, the wider the frequency band is. So Q determines the amount of bite I take out of the frequency, so to speak. Paragraphic equalizers combine the functionality of a parametric equalizer along with the handy user interface of a graphic equalizer. Unfortunately, the old analog outboard equipment was expensive and difficult to make, so there were very few of them manufactured. Using modern software technology, however, paragraphic equalizers can be an effective and efficient tool. Okay, let's consider audio filters. Audio filters are just the components that make up audio equalizers. In other words, it's the audio filters that actually do the equalization. One could say very generally that anything that changes the timbre, the harmonic content, or the pitch of audio is an audio filter. Another way to think about it is that an audio filter is, kind of the traffic cop for audio frequencies. It decides what frequencies get passed, and by how much, and what frequencies don't get passed. There are two categories then of audio filters: stop band filters, where frequencies are eliminated, and pass band filters, where frequencies are allowed to go through. Those are the only two kinds of filters in a perfect audio world. However, we know that things aren't always perfect. So between the stop band and the pass band, there is always this transition band, the area between the stop and the pass bands, where the audio doesn't quite get passed and isn't quite stopped. Transition bands represent one of the imperfections of audio filters. A transition band can be long and gradual, or it can be steep and sure. It depends how the filter was designed and what it's designed for. Here we see a first-order filter which is gradual and takes some time for the frequencies to be reduced. Actually, this is a first-order filter, and it rolls off at 6 dB per octave. That means every increase or decrease of 1 octave in frequency, the level will change 6 decibels. This shows a fourth-order filter, where the roll-off is rather steep at 24 decibels per octave. This last diagram shows a 10th-order filter, which is really steep, and the loss here is 40 decibels per octave. So the steepness of the curve is measured in decibels per octave. The more steep the curve, the more phase distortion is introduced. Very high-order filters, known as brick wall filters, are extremely important in digital audio. So looking more closely at a bandpass filter, here we see the band of frequencies that's allowed to go through. This band of frequencies has a center frequency, where the amplitude is maximum. On each side of that center frequency, both higher and lower, there are frequencies where the amplitude has decreased by 3 decibels. Called the half power points, these frequencies define the outer limits of the bandwidth. So the bandwidth of a bandpass filter are those frequencies between the 3 dB points on the filter's curve. There is an important relationship between the center frequency and the bandwidth, and this ratio between the two defines the Q of the circuit, how wide or how narrow that bandpass is. A band reject filter is just a bandpass filter, kind of turned on its head. In other words, frequencies outside of the band rejection are allowed to go through, but those between the 3 dB points are held back, or reduced in level. In summary then, band pass and band reject filters have center frequencies, they have bandwidths, which are the frequencies between the 3 dB points, and they have a Q, which is the center frequency divided by the bandwidth. Well, this concludes Module 10, Spectral Processors. Can you name 3 types of spectral processors? Can you tell the difference between an equalizer and a filter? Can you name the controls on a full parametric equalizer? And tell me what they're used for. If so, please continue to Module 11, Time Domain Effects.